this lecture, I will explain equivalent circuit of a single phase transformer. When we are considering the transformer is operating under no load condition, this is a practical transformer is operating under no load condition. This is the core type of transformer. They are wound the winding on one limb and another winding on another limb. So sinusoidal voltage is applied to the primary winding. It will draw the no load current, and the no load current is a phasor sum of magnetizing component of current and wattful component of the current. This magnetizing component of current I mu bar is to produce the flux, and IW bar is the active component of the current to meet the core losses. So this is magnetizing component of current. And IW is active component of the current. Generally, why we are going for the equivalent circuit of a single phase transformer means we are having a variable terms and as well as the constant terms. We have to represent in an equivalent circuit. If you observe, the supply is only one. That means only one supply voltage, but the currents are two. One current is magnetizing component of current is to produce the flux, and another one is wattful component of current to meet the core losses. I can represent as a parallel circuit. If voltage is 1 and current will be 2 means we can represent the current is divided means we can represent the equivalent circuit, that is a no load equivalent circuit, as a parallel circuit, and the active component of the current can be represented with resistor, and the reactive component or magnetizing component of current or component is represented with reactance. Active component is represented with resistor and the reactive component is represented with reactance. Now the current which is flows through R0 is wattful component of current, and the current flows through X0 is magnetizing component of current. In some textbooks this is given as IM and this is given as IC. Okay, IM magnetizing component of current and I mu both are same, and IW and IC both are same. Now if you apply KCL at this node, I am getting the no load current. So how many supply voltages are required here? Only one supply, that is, let us say V1. If you want to find out the R0, that R0 value is equal to V1 divided by IW, active component of the current. X0 is equal to V1 divided by I mu. This equivalent circuit is also called as a no load equivalent circuit. No load equivalent circuit of single phase transformer. No load equivalent circuit of a single phase transformer. So when we are considering the primary winding resistance is R1 and the primary winding leakage reactance is X1, and the secondary winding resistance will be R2, and the leakage reactance is X2. We are connecting a secondary winding to the load, and the primary winding is connected like this. So the symbolic representation of transformer is like this. Once the transformer is loaded, coming to the concept, when the practical transformer is operating under load condition, once the transformer is loaded, I2 current is flowing through the load, which will produce I2 dash, and that is added to the I0. Once it will be under no load condition, the no load current is flowing through the transformer, and once the transformer secondary winding is loaded, the reflected coefficient is extra current is flowing through primary winding, then I am getting a primary current, that is I1. So we have to represent the no load equivalent circuit in the equivalent circuit of a single phase transformer, and as well as the resistance of the winding and leakage reactance of the winding. If you observe this equivalent circuit, the no load circuit will be missing. So I am adding the no load circuit here. So active component is resistor, reactive component is X0, the no load current is I0, and the current which is flowing through this one is IW, and the current flows through X0 is IB. If you apply KCL at this point, then it is satisfied. I0 bar is equal to IW bar plus IB bar. Once the current is flows through secondary winding, there is a reflected component on the primary. So if you apply KCL at this point, if you apply KCL at this point, it is a phasor sum of I2 dash and I0. What is the phasor sum of I2 dash and I0 bar? That is the primary current which is drawn from the supply. So this is the exact equivalent circuit of single phase transformer. The primary induced EMF is E1 and the secondary induced EMF is E2. The terminal voltage, secondary terminal voltage is V2. Say under unloaded condition, means no load conditions, this I2 value will be 0. This reflected coefficient is also 0. So under no load condition, I2 is 0. The drop across this is also 0, and the reflected coefficient I2 dash is also 0. Then the primary current I1 is equal to I0 bar only. I1 is equal to I0 bar. Suppose I want to shift the secondary winding resistances to primary side. Secondary winding resistances to primary side. R1 is primary winding resistance, X1 is primary winding leakage reactance, and the R0 is a no load active component and X0 is reactive component. And if all the secondary parameters are shifted to primary side, now this becomes R2 dash and this is X2 dash. And if the load is also shifted, you know that V2 by V1 is equal to K. V1 is equal to V2 by K. So we can write it as V2 dash also. So now this one is V2 dash is equal to V2 by K. And if the load impedance can be ZL and it is denoted with ZL, and if the load impedance is shifted to primary side, that is ZL dash, ZL by K square. The current which is flowing in the no load branch is I0. This one is wattful component of current and the magnetizing component of current. Now the current which is flows through these secondary parameters is I2. If you apply KCL at this node, the primary current is now I1, the supply voltage is V1. So here I have a E1, the voltage which is applied across this node is E1, that should be equal to E2 by K. We know that E2 by E1 is equal to K. From this equation we can write it as E1 is equal to E2 divided by K. Suppose if primary side parameters are shifted to secondary side, primary side parameters are shifted to secondary side. If the primary side parameters are shifted to secondary side, R1 becomes R1 dash and X1 is X1 dash. The no load parameters R0 is R0 dash and it is also changes to X0 dash, and the current which is flowing through this is also changes. The current flows through load parameters. And this is the internal impedance of the winding, secondary winding, R2 and X2. R2 is the resistance, secondary winding resistance, X2 is the secondary winding leakage reactance, and this one is V2. And the current drawn from the supply, now it is I1 dash. So this is V1 dash. So we are representing secondary side parameters. The secondary side parameters is now supply voltage is represented as V1 dash. Anyway, the primary current won't change, right? So that I1 is equal to I1 dash. The secondary current is now I2. This one is I0 dash. The primary current drawn from the supply is now I1 dash. That I1 dash is equal to, we have a relation, right? Yes or no? I1 by I2 is equal to K, where I1 is equal to K into I2, where I2 is equal to I1 divided by K. See, this E2 is equal to E1 dash. We have a relationship E2 by E1 is equal to K. E2 is equal to K times of E1. This is K times of E1. So the current which is flowing through R0 dash is IW dash, and this one is I mu dash. We can apply the KCL at this node. Finally, I1 is equal to I2 bar plus I0 bar. But by observing these two circuits, we can't add R1 and R2 dash directly, X1 and X2 dash directly. Why? Because in between the middle branch and no load branch is present. So that's why we are going for the approximate equivalent circuit with some assumptions. Approximate equivalent circuit. The no load branch is shifted to left side, that is nearer to the supply or across supply. So now this one is R1, X1, R2 dash, this is X2 dash, ZL dash is equal to ZL by K square, and V2 dash is equal to V2 by K. And the current flows through the secondary winding is now, it is I2, this one is I0, the primary current is I1. So we are modifying this circuit. This is the secondary parameters are shifted to primary side. R1 and R2 dash. Now you can directly add. From this we can write it as R01 is equal to R1 plus R2 dash, and X01 is equal to X1 plus X2 dash. So R1 plus R2 by K square, X1 plus X2 divided by K square. R1 plus R2 by K square and X1 plus X2 by K square. These two are added and these two are also connected in series. And here across this no load branch is now E1 is equal to E2 by K. If we are shifting the no load branch across the supply, the I0 value increases. I0 into Z1. This no load impedance drop. Here we are not considering the Z1, that will be shifted to right side. This no load impedance drop will be neglected. If I0 increases, the core losses is also increases. If we shift the no load branch to across the supply, the I0 value increases. It means the core losses are increased. In this circuit, if you observe, suppose I am applying a 10 volts and the 1 volt drop, let us assume 1 volt will be dropped across this R1 and X1 combination. The remaining 9 volts will be applied across the no load branch. But here if I am applying 10 volts, entire 10 volts will be applied across this no load branch, 10 divided by some impedance. As the voltage will be increases, then I0 value is also increases and the core losses also increases. So that is the assumption. And if it is shifted, that means all the primary side parameters are shifted to secondary side. So this is R0 dash, X0 dash, and the no load current is I0 dash. And the primary winding resistance now it is R1 dash. Leakage reactance is now X1 dash. And the secondary winding resistance is R2. The leakage reactance is X2. And the load side parameters is V2. And the load impedance is ZL. Load impedance is ZL. And this is also E1 dash, E2. That E2 is equal to K times of E1, and the voltage is also changes to V1 dash, and the current is now the primary current is I1. This is approximate equivalent circuit with respect to secondary, and this is approximate equivalent circuit when referred to primary. In this equivalent circuit, we are representing the fixed parameters and as well as the variable parameters. R0 and X0 are the fixed parameters. That means the no load current, no load branch is same. The current which is flows through primary winding and the current which is flows through secondary winding, both are variable. Because the load current changes, I2 is also changes. The supply current which is drawn from the transformer source is also changes. I square or losses changes, and the leakage reactance is also changes. Okay, so we are taking a maximum leakage reactance. The flux which links either primary winding or the secondary winding, but not both the winding, is called the leakage reactance. If you observe this equivalent circuit of a single phase transformer, all the parameters are mentioned.